Okay, boom. Okay, so we're live now. And that's it. I don't have any agenda. Sometimes I throw out a starter question. Sometimes somebody else is excited to have a question answered. Anyone want to go first, or I'll throw out some junky thing to get the ball rolling? Yeah, so fine. Oh, there's another body coming up here. Let me throw in one more person while people figure out what they're going to say. Yeah, so I crossed a threshold with unifying Hindley-Milner and my flow lattice-based forward flow typing theory. And I claim I have an implementation that is, correct in theory and in practice is full of bugs. So I'm busy, pulling bugs out. But I actually have something that claims it does parametric polymorphism and also, partial evaluation and aggressive forward propagation of things. It's definitely strictly stronger than either one independently. I don't know. That was my 2 bits of progress on Thanksgiving and that kind of stuff.
But what does it mean to be stronger than partial evaluation? I mean, I can get why it can be stronger than Hindley-Milner because it's very restricted, but partial evaluation is a pretty big bucket.
What I mean is okay. So when I say partial evaluation, I am referring to a forwards flow propagation of types of type values, types. And, my forwards flow is sort of best I've ever seen. I don't claim it's the best there is, best I've ever seen, but it does not let me relate types between 2 independent pieces of program, which the parametric polymorphism does. So they're different. So one is the types at a point in the program, and one is a relationship between 2 different points in the program. And so I claim they solve for independent problems. So you're right. So I give you a mapping call. It does a standard list map over lists of X's and Y's, or lists of whatever, right? With my forwards flow, if map is called once, I get its precise type, and including the recursive list type and the function, and it gets the correct answer. As soon as map's called by 2 different guys, it merges at the call site, and the lists become approximate. And so the result list is approximate. It's the merge of the 2 inputs applied to the 2 functions. So you get an approximate answer out. So that's, weakness. Strength for the... Sorry, go ahead.
This means everything can be polymorphic, right?
That's the intent. In a what I'm calling a forwards flow typing, which looks a whole lot to me like, I don't know what I'm going to call it. I have no parametric. Everything is a grounded type, but is much more precise than sort of the usual thing. So it's not just ints and floats. It's everybody, including structs and struct field names and types and nested types and recursively nested and loops and all kinds of shit. But it's still a forwards flow typing, and it doesn't relate 2 different fields as being the same type. Instead, they're both grounded, and the ground types are the same. And I'm, like I said, I'm up to, without some sort of parametric polymorphism, I'm up to discovering types on loops and types on recursive structures and types for, map over tree structures automatically being discovered with just forwards flow typing, but not if I call mapping functions with 2 different trees, because 2 different types trees.
How do you resolve this aspect? I can see how you can do this with context sensitivity in your existing analysis, but it sounds like you're doing something somewhat different for this case.
Yes. So at the point where Hindley-Milner says these 2 things are the same type because they have the same type variable under the hood, but the forwards flow says I had to merge at a call site and post the call site at the return. So the merge point for the call, two different calls call one function. So it's a merge, a classic function merge. they're passing in two different lists, and the tails of the lists all merge as well, and then I get a list of merge results. I go through some call, and then I split the call sites to the returns. Hindley-Milner at that point says, on this arm, the type of the return is related to the types that came in, and on this arm, type of return related to type of over here. Right? So it lifts at the exit of the function at the return point of the two different calls. It lifts, which in my lattice theory turns into a join. I do a classic join, not a meet, a join on the inputs on either side, and it just sharpens the type. So I get some types here, and they come in, they do a thing, and then whatever the hell comes out. But this type is related to this type via, Hindley-Milner says these two are the same somehow. So it's the function return type that is mapping over the list second element, whatever the list type down here. I get a join, I do a join, and that sharpens it. So that's how I'm combining the results.
So it's as if you inline the body of this genetic function, and
yeah, it's as if I inlined it. The difference being is that I don't infinitely inline. So right now, if I don't do Hindley-Milner, I inline those functions sort of fairly aggressively, but I can't do it infinitely. And if I inline them aggressively enough, and everyone does shallow tree paths, sort of shallow code paths typically, so a modest amount of inlining covers like a huge set of cases, but not everything. That doesn't go infinitely far. Whereas Hindley-Milner says infinitely far. So I'm giving you the trivial map, but you can have, every kind of composition going on, and the depths of things, the type systems can get very complicated, very large, and they're beyond where you want to inline.
So does it mean that you express the relationship of incoming and outcoming types in some way, and then use this in your forward flow analysis?
Yes, exactly. So the some way is Hindley-Milner. I've badly hacked Hindley-Milner in something that makes it look like a work list algorithm with SSA. Fine, that's sort of more mechanical. But I have type variables with points in the program, and they get unified via the rules that Hindley-Milner does. And then when I decide that these two things are unified in type variables, but they have different base types, because they're unified at type variables, I can do a join, and that will lift the values. So yeah, I have type variables for grounded types. I have type variables for Hindley-Milner. One tells me the sets of values that can appear at a point in the program. It can be ints or bool, or it can be floats or strings or whatever. It's a set of valid types, functions of A to B and structs of. And the other one says these two things are related. And when I say related, the limit of the relation is that they have structurally equivalent. That is, if this was a function pointer here, this has to be a function pointer here because they came in and did whatever they do, and that's the relationship. Or they're both structs of the same arity and the same field names and so on and so forth. So Hindley-Milner says, I give you typing equivalence up to some limitation of your function of so much arity or not. Modest extension, okay, structs are included in that, fine. But it's a relationship between two things. Does that answer what you're looking for?
Oh, yeah, more or less. So just to summarize, so it sounds like you have some way to accumulate the results of the type flow through functions, express it in some way, and then use it in your forward flow instead of inlining it somewhat like interprocedural analysis. I
am doing what Hindley-Milner does, except I've reworked the algorithm to do it in a work listing style, but it's the same basic thing. So Hindley-Milner comes along and says, in various points where you have call sites and applications to calls and functions, I generate a structural type, if you will, which is I'm a function of A to B, but A is itself a function of blah, 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 and B is and whatever, fine. And you get a complicated type variable relationship. Then he unifies at these points, and the unification is sort of straightforward. It says these two things are supposed to be equal. One's a bare type variable, one's a function of A to B. So I unify them by claiming that the bare type variable is actually also a function of A to B. It's the same guy, same function, whatever. This is classic unification. Sort of it's Target union fine all over. that gives me that set of relationships between nodes. And then I apply it by doing the joins, as I was saying a second ago. Is that, yeah, and it's not, you're saying I have some way. I have some way. It's very much Hindley-Milner in terms of its strength and its spirit. It looks different because I had to go into a work list algorithm, and Hindley-Milner does a one pass over a tree structure, which doesn't work when I'm doing abstract interpretation. So the things that haven't been said here is what happens when my program changes shape to the Hindley-Milner's unification? And that's sort of in my head, that's the big algorithmic question. Because I come along and I say, in my abstract interpretation, this if test is true or false. So the other half is gone. And Hindley-Milner said, I unified the false and the true branches as part of my normal unification process, but one of them's gone. What does it mean? And you know, the easy answer is that the gone guy is actually dead, and the unification with dead doesn't do anything useful. So you just cut it out, or you just ignore it. I don't know if that helped.
Yeah, I guess my main question was, how do you combine this with forward flow analysis? And
yeah, the big piece is I'm joining post call site. At a return from a call, I join with the types that I got from the pre-call. It's actually, it's not even that, it's not the types you get from it. You join with whatever Hindley-Milner says he got out of the call. That joining behavior more or less effectively sharpens you according to the call path. But if you have long, deep nested, complicated, you know, combinations of functions and compositions of whatever, it's not obvious as to how they relate. But that's where I go from Hindley-Milner into forward flow. Then there's a reverse question, how to go from forward flow to Hindley-Milner when I'm making changes. And the obvious one is I have dead code. And the not so obvious one is I do type specialization, which is effectively code cloning. That one's easier. As soon as I clone code, I have a bunch of new type variables for the new clone code, and it just reunifies all over again. But now in the new context. So I do limited inlining for type analysis, usually to make primitives bottom out, so I don't have to have an extra bit carried around the primitive to know that it's a primitive type. I don't have to make a reference out of a primitive. So I do inlining, and it impacts Hindley-Milner in sort of a more obvious way, just to get new, fresh variables. The harder one in my head is in the dead code, and also what to do post call sites. And it's not done, it's a work in progress. And you know, as soon as I expand my test cases beyond something else, I find a new bug, but the bugs so far are sort of obvious. I just didn't get this piece right or that piece right. I think the theory is good. Knock on particle board. So that was a stunning silence. It's a work in progress. I think people want to play with it, and it's not in a playable state, really. And you can download and look the code, you can run the test examples. But it doesn't go very far until it falls over something. But I think the theory is sort of correct.
Yeah, I can chime in. I have a completely different topic to discuss.
Yeah.
I was curious what everybody's opinion is on parallel garbage collection. The context there is that in my language, I use parallel garbage collection, not concurrent. But I've been sort of reconsidering that. It requires a fair bit of complexity. And because in my language, all tasks or processes are isolated. Their heaps are also quite, well, maybe not necessarily quite small, but much smaller than in a language where you have a shared heap. So I'm kind of curious what sort of people's experiences and opinions are of it.
I went down this path a whole lot in a lot of different contexts. So obviously Azul systems, which was, you know, concurrent parallel, but pre-Azul systems at Sun, we went through the parallel GC path. And then I did a lot of thread local GCs as well. So the easy answer is, as soon as you have a parallel program producing garbage, you have to have a parallel garbage collector to keep up, or you'll just be forever garbage collecting. So you must have parallel garbage collection if you have a parallel program. You just must. So now the question is, do you want to be concurrent and parallel, do you want to be thread local, or some other kind of thing to get your parallelism in? I did the thread local thing at Azul in an effort to actually get better cache footprint, not actually to do better GCs, but better cache footprint. Was modestly successful on any large busy Java program, modest being, I tried hard, I hit 70% on big busy web servers would be thread locally allocated and garbage collected. That was not good enough to beat the Azul generic collector. So as a performance thing, it didn't work. As a cache locality footprint, it had a modest effect, which we decided wasn't worth the complexity and we bailed out on. It was there, it was positive in the modest. These days, x86s have bigger caches and more bandwidth. That trade-off may change. But as soon as you have a program which produces garbage that leaks, and I don't know what your language and how people are using it, but in Java, really quickly, a lot of things want to leak. Your heap gets big, and then you have to have a parallel heap collection, parallel main heap collection. So always you have to have a parallel main heap collector. And now a thread local variety is an optimization. And as all optimizations, you know, I claim that second order, go get the first order effect, get out of a parallel main heap collector. If you have a language like JavaScript or PHP, where they are strongly single threaded and the shared requires some sort of custom, you know, foreign function interface to get actually shared, that's a different story. Then it makes sense to do thread local GCs. And there's a bunch of things you can do with thread local, to turn thread local into stack local, to turn stack local into, you know, in registers that you can all put support into and make a lot of progress on. But if your language is more like a general purpose programming like Java, you should expect to leak into the general shared heap pretty aggressively, and therefore you must have a general parallel collector.
Right, yeah, so I can see like, well, really any language with shared memory where it's used for bigger application, it kind of makes sense, because at some point you're going to get a heap size where even a concurrent collector probably just can't keep up.
Oh, totally. Yeah.
But so for me, there's this use case where, similar to Erlang, each process is fully isolated and they're garbage collected independently.
And you're good. It's the when you have people writing code that can get shared sort of by default. In the common cases, they have a big ass hash table for caching. It's a web server and they're doing caching. And they want to have a common shared cache across threads that are serving multiple copies of roughly the same kind of work, so caches are effective. As soon as you go there, you leak like hell.
No, exactly. So that's been kind of my suspicion, I suppose, is the best way of saying it. Because I implemented parallel collection because the collector algorithm IMIX that I'm using, it's parallel, at least in the paper they made it parallel.
I'll get you in a second, Trolls. It's a good question.
Sorry?
I Trolls threw a good question out, but keep going.
Oh. Let me quickly check. Won't a parallel concurrent coupler easily risk constantly efficient work instead from cache?
Yeah.
Yeah, basically.
No, you're wrong. The Azul experience is if you do your concurrent parallel collector right, it does not evict the working set from cache because it doesn't have to touch it that often. You always run the garbage collector in a separate thread. So you said concurrent, but it's not running with the same thread. So it's generally on a different core. So it's generally got its own L1 and in some of L2. So on Azul hardware, of course, we ran all the L2s separate from the mutator, so they didn't get polluted there. But on an x86, you don't do that. Your L2 has to hammer it. Yes, so it bangs away at the shared lowest level shared cache, but not enough to harm the main thread's sort of fast forward progress. You're much worse off because the fact that you are having to do a GC cycle, you have already allocated. As soon as you allocated, the thing you allocated was guaranteed not in your cache, and you sucked it up already. So the main cost in the collector, the garbage collection cycle, the main cost is the mutator allocates with a new, and that's a lose right there. So that's the main cost. The actual background collector, man, it doesn't hurt you that much. The thing that Azul did that brought their latencies down was they added a read barrier. Read barriers cost is now on the order of, it's under 5%, but it's definitely measurable. But that's typically small change compared to like an old school stop the world collector where you look at the pause times and stuff. Small change compared to that. If you have a concurrent collect, some of the current collectors out of Sun have more expenses to them, and they'll hit you harder than 5% already. But it's generally, my experience is it's not the working set eviction. So what I was trying to do with Azul with stack allocation was to save that 5% of, working set allocation or whatever the number was. And it turns out to be the read barrier was more cost. If you didn't do the read barrier, but you had a good concurrent collector, which some of the Sun ones are getting, they still suck on the max pause time. That's the issue with it. If you don't have a read barrier, your max pause time suck. Your average pause times can be pretty good. Your overhead for banging on the working set of mutators typically not too bad, depending on how they structure the barrier. But the max pause times suck. So if you're not real time, you don't care, and you just live with it. It gets herky jerky occasionally. If you want to be high frequency trader, you want to have a real time application, you want to fly a drone, got to have low max pause time. And now you need a read barrier, and now you pay a read barrier cost, and that exceeds the other costs.
Right. Yeah, because it's, I think for me, the sort of best reference I have is Erlang, because it's a language that does concurrency fairly similar. But Erlang has a pretty, I wouldn't call it exotic setup of managing memory, but quite different in that they they garbage collect by default, but then I believe if objects reach a certain size, they start using reference counting. And I think that's mostly in optimization, so copying them around becomes cheaper.
Yeah, that's an expensive way to solve that problem.
Right.
Most of the collectors, that say modern collectors, just simply put big objects in a big object space, and they quit moving around.
Right, so that's one option. But I basically started looking around. So, okay, I can't be the first one to run into this. Like, I don't believe that.
Hard,
but there is
a problem for 20, 30 years, production use.
Yeah, what I basically found is that there, all these sort of, apart from Java, all the mainstream languages, they seem to be moving towards concurrent and incremental if they already don't do that. So Ruby, for example, is a fairly recent example where I think at this point already, like 2-3 years ago, they moved to, I think it was incremental collection. And you see this with a bunch of other languages, but even the more recent ones, like let's say Nim, Pony, and whatever other ones, they seem to generally lean towards concurrent and maybe incremental mark and sweep. And I think Java's the only one of these that comes to mind, and I'm probably wrong there, that has a parallel collector. But from what I could find, the opinions were a little divided on it.
As soon as you're concurrent, you're 90% of the way to parallel. Fucking just go parallel.
Right. And that's also kind of what I noticed, because you need the same sort of foundations for it to, concurrently move objects around, etc.
Yeah. Yeah.
And so I was kind of looking at it from the angle like, okay, the parallel collector requires a fair bit of complexity. And that's the...
Well, okay, I guess I've been on that path a bunch of times. In my head, it doesn't. You have to walk with multiple threads. Most of the time involved here is actually walking the heap. You said mark and sweep. Not everybody wants to play mark and sweep games. Most of the good, fast, concurrent guys are not actually copying shit, not very much. They copy to defragment, pages kind of thing. But it's concurrent walking. Okay, so you need a concurrent walking. How do you parallel walk a heap? Well, you have to have some notion of who's walking what. You have to have a shared work list. These are all, now you can grab utilities for all of these things that are reasonable. You need to have, actually in a single core, that's not gonna help you. In a single core, you wanna do multiple paired prefetches because x86 prefetch, bandwidth exceeds what you can get from one load, that's fine. To know that you've marked already, you have to use CAS to set some kind of mark bits down so you don't completely overmark. But this is all in a background thread, so it doesn't burn the mutators to use a CAS instead of a load modify write kind of thing. By the time you go concurrent, you typically also have to use a CAS because you're fighting with the mutator. So by the time you've gone concurrent, like I said, I think you're 90% of the way there to being parallel, and you just need a little bit of hook for launching parallel, walking threads and doing the join at the end and proper load balancing across, for which you can get libraries that just do that.
Yeah, so I have all that in place. Like it actually works fine.
Okay.
But it's more like I basically looked at it and sort of asked myself the question, like, okay, is this truly necessary? Because eventually, I would like to have a concurrent collector. Let's say 10 years from now, because it's still very far off. You had a
concurrent collector going now. You have a parallel collector.
No, I have a parallel one.
Gotcha.
So it's a parallel, and it will stop the process that it's collecting, but all the others can keep running.
That was the default Java collector for almost 20 years, like 15 years, the default parallel collector. And it worked great obviously for a very long time for a very large spectrum of people.
Right. Yeah, and so my issue there is like, okay, I want to eventually have concurrent, so we don't have to stop these processes. And there's the complexity with parallel is mostly around determining, how many threads do we need. Right now, I take a naive approach and I just say all of them. And then there's the problem of, when is work finished? Now, I take I think somewhat common, but also naive approach where if a thread can't find work, they just self-terminate.
Yeah. They'll look at, I'm fork join, right? Doug Lee's fork join framework. They'll do that for you.
And that's essentially what it does. But it's this process where, at least the way I look at it, it works when it works, but it's quite unpredictable in that, if timing is right, threads may prematurely stop working and, your performance can degrade and that sort of thing.
That kind of, so that's the heuristics on you ran out of threads and you had more work. So you two ways to go, and they both amount to the same thing. One is respawn another thread. When some worker thread looks at the list of work to do and says it's big, he spawns. He forces another thread, right? The other version is threads don't go to sleep quite that quickly, but they have an exponential tail off and they just start sleeping for a while, and then they wake up and see if there's more work. Right, you got one guy and he's got 10 things and he's like, no, don't, everyone go away. Don't steal from me, go away, right? Then suddenly he cracks open the last link to a large chunk of work and he like spews work all over the work list, and the work list grows to 1,000 to 10,000 roots, and now it's time to get threads back in. How do you want to do that? Like I said, fork join, Douglas fork join, he's worked on this for a long time. I think he has heuristics that are reasonable. I think in all these things, exponential back off, either by killing the thread and restarting it or by having them sleep and then wake up, is the way to go. I did a similar effect when I was doing compilation thread pools, where I spawn threads while the work list is big, and then the work list gets small, they want to exponentially back off. And obviously, if you're the last dude running and there's still a lot of work, somebody has to decide to kick another thread up. So there's however a kick a thread up works. If they're all just sleeping, then they'll kick up themselves. If they didn't actually sleep, then you had to go wake them, then you got to do something. But you have to have something there because it's bursty. It can be bursty. The worst case scenario is bursty. So worst case scenario, you got to kick it up. I think the collector just had him hot spin. It was okay.
Right. Yeah, I think for me, what played a role is that, the state of my language it makes it a little too early to do benchmarks because you only have synthetic ones. But I found it hard to reproduce like any sort of tangible benefits from the parallel collector. But that's this problem of you don't have like an actual application to test it on.
That's what I mean. You don't have enough work. So don't worry about it. If you're writing a toy language for yourself and you're the only consumer, you're having fun. Do what you're gonna do, but don't sweat.
Right. And so right now this isn't a problem. Like it works. It's it's there. What kind of kicked us off was the language has its own schedule, like Erlang and Go, etc. And I think once every 6 months or so, I reinvestigate that to see, hey, can we today finally spawn a thread per request basically and get away with it up until tens of thousands of requests, etc.
Like
through that, I sort of
thread or like a Yeah,
No, like an OS thread.
Yeah, okay.
And so through that, I sort of ended up here and say, okay, well, let's say we spawn a thread per request. Then we can simplify some parts of the garbage collection because we can do that in that thread instead of having to first send it up to separate one.
You want to spawn a thread per request because you want to have the garbage collector. This should be
no. This was just sort of a thought experiment. Like, okay, if we could do that, for example, if we had infinite performance, what would the sort of technical and maintenance benefits of that be?
Oh, if threads were cheap, you'd spawn a thread per request because hell.
Yeah, but so through that, I ended up with the parallel collector because what it does now is this a certain number of garbage collection coordination threads, as they're called, one for every core at this point. And each of those has their own pool of threads they use for tracing, again, equaling the core count. These numbers are like completely picked out of thin air. But so I thought, okay, that works because we have fixed number of threads. So, yes, you start with, let's say, 64 threads on,
64
more, because it's, core count times a couple of times for different pools. But the number is fixed, so that's okay.
I would claim you should have core count and thread count equal to core count, period, stop.
Right, so there's a couple of pools, and they all have a thread count equal to the core count.
Right. And as long as the pools are not running in parallel, you're fine. If they're running in parallel, I think something's going not what you want.
Right. But so through that, I realized, hey, if we start doing threads per request, if you then for every of those threads have a pool equaling to the core count, then you end up with way too many threads. So you need a different approach.
No. If you are collecting the garbage from one thread, reasonably one GC thread can keep up. It's if 64 threads produce garbage that you want 64 threads to clean it up. So if you're in the zone of, I'm doing a thread local concurrent collector, one thread is doing user work, mutator work, one thread is doing GC for the one thread, then you probably, given the ratio of garbage collection speed versus allocation, you probably end up with a, 10-to-1 or a 5-to-1 ratio between those kinds of threads. And so you can get away with having, 50 mutators and 15 collectors and still win the day. That's getting into control theory and overdamping system flow and stuff, which the Zoll collector totally actually does that math for how much and when to start GC cycles and how fast to go and stuff like that. That goes into, I want to say, I got control theory in my double E undergrad. But it's just a little bit of hysteresis on how fast you spawn things up. So if you're in the zone of mostly the garbage is one thread, conceptually, I'm independently threads, and we don't pass garbage. We don't pass objects between threads except under very carefully constructed circumstances. Then you're doing a single-threaded collector. And actually, a single-threaded collector can reasonably do not concurrent even, because he just collects on his own garbage, and he's reasonably fast about it. And the other threads will keep running because they're going to collect on their own cycle. So it doesn't actually halt everybody. It just halts the one thread. Or at least that's the model I went after, and it worked out nicely. And because it's single threaded and one thread's doing garbage, because no garbage is hot in his cache, and he has no contention with anyone else. It doesn't have to use CAS instructions. It's all way the hell fast to do a local collector. And then you have all the different problems of a local collection, which is, one thread out of whatever gets a really big heap, and he really does want a concurrent help to doing it, or parallel at least or something. And then I still had issues where I at least had things leaking. And so periodically I'd have to stop and go escape a whole crap ton of stuff to the general heap. And that made my life more complicated. I'm hearing a mixed story. You actually running the threads cannot leak or share heap?
I'll cover it. So there's a couple of different thread pools. There's one which will run your regular processes. Let's call it the main pool. And this is where code runs by default. It's a process, and it can be moved across threads, the Erlang Go, whatever model. There's a separate pool for blocking tasks for which there's no non-blocking equivalent. So file IO without IO uring, for example. or writing just standard out, stuff like that. And the standard library provides the means to move processes between these pools when necessary. Then there's a pool for the garbage collection coordination. This will scan the stack, figure out, do we need to move objects? Do we also have to do a mature collection, etc. And then each of those coordinator threads has its own pool of tracer threads, and they will do the actual tracing of the heap, marking, etc.
But they have their own tracing threads because they're tracing a other user thread.
No, so with each, the model is a little finicky because the setup I had before was even weirder. So this is sort of a in-between step best case for what I could do now. But so basically the way it works, the coordinator will prepare everything, scan the stack, etc. It will take its pool. It will schedule all the objects to the routes. And then it will basically wait for those tracers to finish. And then it will do some cleanup, reschedule the process.
So a tracer thread traces one worker thread or all of them?
No, so given a particular pool of tracer threads, they will all operate on the same process or the same mutator. You won't have a tracer pool operating on two mutators at the same time.
So it's a tracer pool. So the coordinator thread does one coordinator per one worker thread? Or one coordinator covers multiples, or multiple coordinators?
One at a time.
So a coordinator thread, one at a time, picks a user thread, does a one-time pass, such as discover the routes, and otherwise sets up. He's expecting now to be thread local GC, not a shared heap. He then spawns enough workers to trace that guy. Yeah, okay. Yeah, okay, fine. Right. I would kind of expect a young gen versus old gen collection of a single thread heap to be modestly small and not need very many tracer threads before you're spawning tracer threads that are fighting each other for work.
Yeah, that had been my experience where if I remember correctly, and this is a while ago, I found that between 1 and 4 threads, there was like a minor difference in performance, and this was on an 8-core laptop, so basically the metrics are bullshit, but there's a small difference, consistent enough, and then beyond 4 threads it just kind of either stayed the same and then at some point just dropped off, probably because of contention. But it's because all these threads are isolated. Once in a while I think like, hey, maybe it'd be nicer if you just get rid of the parallel collecting, make the code a little simpler, because it seems the performance is not that at least not worth the effort.
So your parallel stop a thread at a time, or do you stop all threads at a time? You stop one thread at a time?
No, just one.
Yeah, okay. That's actually pretty close to what I was doing. I was stopping one thread at a time, except I was having the thread do self cleanup instead of parallel. Like as soon as you stop one thread and you get rid of parallelism, you're down to the zone of the one stop thread can just do the job himself, and it's all hot in his core. That's where I went. But I had to deal with a large shared heap also. Which is...
Yeah, in this case, the thread itself, because the process threads basically, while a process is collected, those threads will just start running other processes. So I do have to move the work to a separate thread. Otherwise, you might block application code.
Oh, you have worker threads who are doing like a fork join. They have a work pool. The current task they're working on needs a GC to carry on.
Yeah, so
no, I would, okay. So I claim that you have a different thread. I would claim you want to change your thread breakdown, like really have the worker thread not pick up more work, and have him just do his own collection, and he is his own GC coordinator thread. And then because he's busy doing GC and you still want to carry on elsewhere, you have a bigger pool of extra threads, some of whom are stopping on a current task because they're doing GC, and some of which just go back to the pool and grab. Now, once this guy's doing GC and all your cores are otherwise busy, it doesn't matter to take another piece of work off the work queue because no one's gonna make any forward progress because you're all busy anyhow.
Yeah, that's something like I thought where you could do away with these coordinator pools and just have the mutator OS threads do the collection of your mutator green threads.
If right, yeah. Don't have a shared common large heap. Yeah.
I think what bothers me is I haven't really found any sort of solid material where people compare that approach to the approach of moving these green threads to a separate thread for collection. Because in theory, the performance wouldn't really matter, right? If you have, say, 4 cores, you can only essentially do 4 things in parallel. So adding more pools doesn't matter.
Exactly.
But it's one of those things where I think opinions are quite divided.
Yeah. Oh, okay.
And so I prefer to have some paper that says, no, we tried this out, and this works or that does.
All right. Well, I'll claim I went both directions, or at least some of what you said in both directions, and there was sort of an obvious break. If you're strongly single-threaded, work is strongly single-threaded, doesn't share between each other, I would not be parallel. I would be, or concurrent. I would be single-threaded, stop the world on my one thread. The other threads carry on, do what they're going to do, but you still have to have generations, because some one thread has a large old gen, maybe several do. Somebody has a large old gen, and so it's slow to collect. So you want to collect rare. If you're looking for max pause time reduction, then you actually have to go down the path of parallel. But you could do parallel, stop one mutator and be parallel on his tracer, and the one mutator just stopped. There's no point in grabbing more work from the work pool unless you have cores out the wazoo, in which case maybe you actually want more parallel collection, or you just want more workers, so some other workers not actually stop for GC. That was the Azul finding, was that as you added cores to a server, it became less and less likely that you actually had work for them all. And so it was commonly the case that it was, yeah, you could throw up another GC thread, and it didn't really hurt, didn't really matter. You could run servers flat out, but that was not commonly done in production. So the common case scenario was, I had spare cores. If I had enough work to go around, I would just want to spawn another one. And as you pointed out, by the time you get past a couple, at least in your single threads worth of work, there wasn't any work for them to do, and you're losing ground, and you have a lot of work for parallel. But somebody somewhere either takes a big stall or has to be parallel. And where do you want to do that? Given a lot of single-threaded work that's independent, I'd stare hard at.
Very sad to have missed the first part of this conversation.
Being single-threaded. I'll summarize, and York can tell me, but we were talking about GC opportunities, or GC, how to best split up work between mutators and GC threads. And I'm coming from the zone of, it's Java, everyone leaks to the shared common heap. You have to handle a large shared common heap. And York's coming from, I'm an Erlang-ish, Go-ish thing, and most of my work is actually single-threaded. And do I want to be a parallel collector on a single thread? And I'm independently collecting on my threads separately, as opposed to a stop the world. Then do I want to be concurrent as well as parallel, whatever? And so we were going back and forth of, by the time you're concurrent, you're 90% of the way to parallel. Actually, I think concurrent's more work than being parallel. And then if my working zone is mostly single-threaded, do I even want to be parallel? Just stop that one thread. Some of those threads have big heaps and they get slow, but maybe I don't care because other threads are making progress. That was the juggle.
In a sense, the challenge that we have is that the history of computing was largely single processor, single thread, and everything was built up around that. And so
20 years now,
the history, the 50 years of history is now the anomaly. So everything was built up around an anomaly, and people can't quite wrap their heads around that.
Yeah.
So I
still went parallel too soon, and there wasn't no market for it.
Well, I've been struggling with some of the same questions. So the model that we started with is much more Erlang-ish as well, and that there is no shared mutable. And as soon as you get there, the entire your entire playbook changes dramatically, because there's nothing more challenging than shared mutable everything, where everything is the same. Is it immutable? Is it mutable? Same. Is it this thread or that thread? Same, right?
But if you have shared but not mutable, you still have an issue that you have to find the dead stuff in the shared, which can be large. You want to be parallel, but as soon as you're not mutable, boy, a lot of issues go away. The whole concurrent issue goes away.
But you can share immutable objects by copying them.
Yeah, right. No. I'm not saying that. I'm saying.
So that's a dramatic difference between shared and mutable, where you cannot share them by copying them. If it's shared mutable and you have two copies, you're screwed.
Yes. I'm sorry, but you said you don't have any shared mutable.
Correct. We have no shared mutable. But so with immutables, so
can't do it.
So the benefit of having mutability kind of confined somehow to some zone is that you actually then have the choice. Each of your threads could have a completely different garbage collection algorithm, could have a completely different. So you can basically at that point, you could have one thread that's running 16-bit code and another thread running 32-bit code and another thread running 64-bit code. You could have one doing a slab allocator, another using a heap, and it's like you can pick and choose. But with no shared mutable information, you have no collision on, there's no chaos.
When you cross over, when you have to hand things off to people, that's a well-tracked event, and they have to agree on the shape and structure of what they're looking at,
right?
How the pointers are laid out and all that kind of stuff.
Right.
Handle. But you're
Which is much more like a distributed system, except it just
Yeah.
happens to be all inside the same CPU.
Yeah. Instead of opening a socket and jamming it into serializer and deserializer, you have some more efficient thing, but there's a known handoff point, and the user is responsible for realizing that there's a known handoff point. Yeah.
In York, this is Inco, right?
By that model.
Yeah, so the setup I have is very similar to Erlang, that all processes are isolated. Sharing involves copying. There is a global heap, but it's permanent. It's not garbage collected, and it's mostly used for classes, constants, things that aren't supposed to change by the user.
So I claim the obvious thing missing here is that you have a shared common cache for people doing parallel irregular workloads. Standard web server. I have a DB cache. I went to the DB for this thread, I went to DB for that thread. Most people are asking for the most of the same things. Mostly the DB hits, I want a cache. I want a shared common cache. How do I do a shared common cache if there's no shared memory?
Right, and so that I don't have at this point. Erlang has what do they call ETS? I think they call it. It's sort of a key value store, I believe, shared.
There's some basically baked into the language a specific shared common cache. Baked into the runtime support. Yeah.
The thing there is that works for Erlang because it's immutable. So you can safely share because you can't mutate it. But Inco is mutable, and that opens a can of worms in that area.
You can't type it as immutable.
I gone down the path of trying to work that out, but you run into some issues where, at least at the time, I still had initializer methods. Constructor methods. I always mix them up.
Yeah.
And the presence of constructor methods makes immutability very difficult to add. Let's say, for example, you have a syntax where if you give an argument a type, it defaults to immutable because that's the safe default.
Yeah.
And then let's say add immutable keywords to make it mutable.
Yeah.
When you have a constructor method, the object it operates on has to be mutable because it has to assign fields to it.
You've already made the object, but it's mutable, but it has an existence.
Right, but so you have this problem. So okay, you have this rule where you say
can't
a
publish
mutable field can be. Sorry, let me think what the model had. So I had this model where a immutable type, because the mutability was made part of the type, an immutable type was not compatible with its mutable counterpart. So in other words, you cannot pass an immutable array to something where you expect a mutable one. Other way around, fine. You get this problem where within a constructor method, to assign its fields, those fields would have to be mutable because otherwise you can't assign them. But that means your arguments that you accept also have to be mutable because you cannot assign an immutable argument to a mutable field. And then you have this problem where if you want to construct your object, you as the developer have to pass your arguments as mutable.
Right.
And so very soon you end up with basically everything being mutable anyway.
Yeah. And you have a couple weird ones like if you do a circular linked list, how do you build a circular linked list out of immutable objects? Right? So let's construct the head.
Yeah.
Now it's immutable.
Yeah. You can't
construct the next one. How do I change the head to point to the next one? Okay, right. So it's like
that's why I went to final stores instead of final fields, so I could construct a circular list and then have it be immutable.
Right.
But I have to do flow analysis on final fields to make that work.
One step towards that, what I did recently is I ripped out constructed methods and I basically added record syntax to it, and then you use factory static methods to do your work. It's not quite there yet, but it's at least, one little thing less to worry about. Solves a bunch of other problems too.
Can you play the game of just casting? Just basically both. It's all final now.
You could do that. You could maybe have special compiler tricks where it says, oh, under these circumstances we know that it's fine.
Right. I mean, I went with compiler tricks, if you will, but I put it in the language as a type system. But basically, I recognize there's no more rights. But I'm saying something different here, and that's just simply, I want this thing to be immutable after a little while. So there's a point where I declare I'm done, and the user adds an annotation says it's immutable, and that the default annotation is at the end of the constructor, it's immutable. But that doesn't work with the circular linked list guy. So then you have an annotation saying, oh, it escapes the constructor immutable, and then a little while later, here's the immutable point. And can you do something with that?
Right, and so I think the conclusion I reached there, there's a language called Skip, I think, from Facebook, where it's one of the few.
Oh, a link. Where's Matt?
Hold on, let me look it up. Was it Skip Lang? I'll add it. It's a bit of an odd language, but I looked at it for inspiration because they have immutability. They do it at the type level, if I remember correctly. So you don't have, an array that can be both mutable or immutable. I think it's always the type. Could be wrong. But what I remember concluding at the time is that you basically need to be able to distinguish between this is mutable, this is immutable, and this is what I own. It's kind of like Rust, where you have move semantics.
But so ownership's different. Ownership's sort of unrelated.
Right, it's different, but it does open this opportunity where with these constructed methods, you wouldn't say, hey, my argument has to be mutable or immutable. You say it has to be owned. And then it doesn't matter what the input is because I will take ownership of it.
Yeah, right.
And that makes that a lot easier, but of course, introduces a whole bucket of other problems.
Oh, okay, fine. I'm in the zone of, I'm doing forward flow on fields, but at the same time, I'm intending to do the same thing Rust does, which is basically a lattice theory on ownership. At the point where you declare you give up ownership, you make you have a typing thing happens that says, if the field was not yet final and I want it to be final, but I'm escaping it, then it becomes read-only for me, but I do not get the final guarantees. So I have a read-only notion for if you bother to escape somebody prematurely. And if you're using it in a context where somebody demands a final, I can say, I want only final things, then, it'll type error on you and you say, go fix your escape. Go close the cycle of your circular structure and then declare final, and then now you have the final thing. You can escape it.
So York, we went through a bit of a similar goal as you, although different way of stating the goal. One of the things that we had as a requirement is that, if you're creating an immutable object, you can never leak a reference to the mutable form of it. So there is no this, so to speak. And it would take me a long time to kind of explain the genesis of the thinking, but what we ended up doing was splitting the construction into 3 phases. But before I explain that, we don't have the typical pointer to vtable C++ approach. We have our handles are composed of a vtable and an identity. So conceptually, so it may have neither, it may have one, it may have the other, it may have both. Most of the time it's both, right? So a hash table is going to have both. An array probably only has one, and int has neither, right? Or something like that. but the idea is during construction, the V table is different. So during construction, you don't actually have a pointer to the object, you have a pointer to the struct. So you have a mutable struct, A space mutable, not immutable. You have a mutable struct that you're allowed to whack at during construction. And that's because the V table that you have, which can leak, you could leak this pointer. It's a pointer to a mutable struct. But then at the end of that construction, which is, you know, virtual and everything else, but at the end of that construction phase, that's kind of phase one, then there's kind of a delineation, and then there's what's called an assertion phase. So basically at this point, you could have user code in there as well, but generally what we're doing is we're validating that the necessary prerequisites of construction are met. Because we don't have null, for example, in the cliff sense, in the put zero everywhere sense, because we don't have null, for example, if you don't fill in a property, it's a construction error. And if you don't like that, then you actually have to explicitly say this value can be uninitialized, right? So you annotate the type. So it goes through the assertion phase, and then there's another wall. And at that point, there's no user code. So at this transition, you cannot, before this transition, there is no this, and after the transition, it's immutable. So this second transition takes it from a structure that was mutable and turns it into an object that's immutable. And so after that second transition, this exists, but it's already immutable by that point. And then so it then goes into a phase, what we call finalization. So in other words, before this is returned to the caller, so someone said new T, right? Before they get their new T back, your user code has one more opportunity to work. So if it's an immutable structure, there's not much you can do, obviously, because it's immutable. But if it is mutable, then that finalization phase gives you a chance to do some additional work before this appears to the caller.
But this at that point remains mutable.
Right. Well, we support immutability and mutability. I mean.
Yeah. Okay. Yeah.
So.
Yeah.
Mm-hmm. But if it's a construction of a const, like an int or a string is a const, by the time it gets to that finalization phase, it's already immutable.
Gotcha. Yeah. Yeah. All right. Fine.
What's that?
I was just I was trying to contrast where you're at with where I'm at, but not I don't have anything big to say I haven't already said.
Well, yeah, I mean, you took a significantly different approach with you basically hyper-specialized finalization to guarantee once and only once assignment, which is pretty cool. Different.
Yeah, it's not once and only once, it's no more after this point. Or the value, no load will see a different value after this point for that field. So actually you're allowed to store the same value over and over again. And you're allowed to have no loads. But no load will see the value different after this point. That's my rule. Currently, implementation will barf at you if you do change it independent of whether there's no loads. If I can prove no loads, then your field's dead, and then that's a different one. And I just throw the final stores away. It's like, no stores at all. It's a dead field. It's gone. But if it's if it's two different stores, or I can't prove it's one unique final store, then I'll blow at you right now. Although I'm claiming the semantics should be if there's no load. Or
do we have anyone? Well, we've got Archer on the call so working on Java. So we have then there's the fourth approach, which is there's no such thing as final. And they're currently arguing that one out on the on one of the records related or Panama related projects where they're trying to now make an exception where they can actually have data that's not allowed to be written twice. So they'll eventually get there.
Because I attempted at Azul, I attempted to do final field optimization and discovered.
And it kills Apache. Yeah.
3 big frameworks all cheated on finals. They all did reflection to yank a final.
Well, we do it the right way now. So we speculate and we can recover if if modification happens.
That's a different one. So there's an as if final optimization, which is totally fabulous. It doesn't need a final keyword or a final semantic in the language at all. It's just, here's the last write to this field. And if it changes, I'll blow up and recompile and reject. But as far as I know, it's the last write I've ever seen so far. And typically that writes of a 0 because it never got changed at all. And now I'm going to constantly fold the hell out of it. And it's all great. I mean, that's what I needed to have ended up doing, and I didn't do because I said, oh, just take finals. People don't actually change finals. Of course they do.
Yeah, there's Apache is basically the test kit for Java. If there's anything bad possible, it's going to be somewhere in Apache Commons or.
Oh God, yes. They weren't alone, by the way, but they were one of the.
They're the worst. Yes.
Somebody in there was doing it, definitely. Spring was doing one where they wanted it to be kind of like a final, but they were doing some game where they decided that they had to change it one last time, or they used final as kind of like our hint to ourselves that we're not supposed to modify it, except we know we're secretly caching under the hood, and the cache updates somehow, and the final actually gets changed. And anyhow, they weren't actually final, and it was bad. Okay, ownership in SSA, right, which is what I'm going to be doing. I'm not doing ownership right now. Borrowed safe interior pointers. That's interesting. Where? Okay, I'll have to read later. Yeah, okay, more good reading. This is always fun out of these things. I get a lot of good reading.
Getting a fax. Holy cow. In 2020. What else could go wrong?
You got a fax?
Getting a fax.
You have a fax machine.
Not technically. I haven't heard this ringer in 2 years. Come on.
Wow. Okay. Yeah, that's interesting. Where did I have a fax machine? We had a fax machine because we were doing back and forth with the patent office, USPTO, and they wanted things faxed. The date of your freaking patent assignment was when they received the fax. So we had to have a fax machine, and then they would fax shit back. Like, never mind email, scan, print, whatever. No. Here is a piece of paper coming out of the fax, sign it and fax it back. So we had a fax machine. Then we had fax spam. We would get locals. I have no idea who was fax spamming, why you would ever, but somebody was fax spamming us with like local food places. And I don't know how they got our fax number, but we would get dumps and dumps. So we had to kill the fax machine unless we knew when it was coming in. Now, this was H2O. This was like 5-7 years ago. We were getting still that faxing. Never mind.
It's amazing what you can do with 1200 baud.
Yeah, good point. Okay, I'm going to read the so we can get back on track here. You guys can talk out loud. You can shut down I'm whining about old faxes. This is like fun, but you know, go for it. You can't text any fields without a method.
Yeah, I did that through syntax. So the fields, it's inspired by Ruby. You access fields using @ and then the field name instead of like this dot.
Okay.
And the parser doesn't allow you to write foo.add bar, for example. It's just straight up a syntax error. So you must go through methods for it.
Huh. No, I don't like going through methods or knowing that I don't know that it got cleaned out. How about that? The fail for me of going through methods is there are times and places where I must know that I'm talking to the bare field because I'm building a current algorithm or I have a very hot structure and I need to know the cost. Hot loops over big data want to have that game, and concurrent algorithms want to have the game where I guarantee you that there is exactly a load or a store here, and which is why I don't like fields I don't like functions I have to go look up. So if there is a variant that says I can inject a function around a field, but if I don't do any syntax changes, you guarantee me it is a bare field access, then I'm okay. I can write that syntax sort of easily. This will turn into a bare field access. Separately, if you also said on access, do this or that, whatever, no, fine. There are fun places where I want to, people want to inject field accessors around stuff. JavaScript's full of these, by the way, and they're useful in places. I've done this with trying to get reactive coding going. There's a bunch of reactive coding libraries, and they want to hook changes to fields because they turn those into incremental DOM updates, which works, but you have to keep it in your head because your callbacks all have to suddenly clue in that what I see is not what I get. And so it was twitchy to code on it. And obviously I couldn't do a concurrent algorithm because that was already the concurrent algorithm support that they were trying to do.
And I'd argue that the whole challenge with the kind of the meta problem that you're describing is that we really only have two fields within, the field is the wrong term, sorry, two playing surfaces within which we can screw around: compile time and runtime. And so you have this thing where you have to choose, some languages choose at compile time what to do, and some languages choose at runtime what to do. And we know if it's a runtime choice, you have a virtuality issue, right?
Well, it turns into performance issues. It can turn into performance. Well, I guess correctness as well. If it's concurrent algorithms, it's correctness too.
And this is, this goes to the final field question as well, and with the writing a final field twice and things like that. But if you had an intermediate playing area, right, where by the time you get to runtime, there's no surprises, which is the challenge with, we'll say Java. I mean, at any time you can discover that there was a class that you weren't aware of that does all sorts of stuff that you weren't expecting, right?
Yeah, but the runtime covered that up. So that one got sorted at a modest cost in terms of huge engineering costs,
huge complexity, right? Huge complexity.
Big engineering costs. Yeah. Once you've bitten that engineering cost, though, that problem's like solved in the sense of I know what to do with it and it's reasonable how to go forward. But if
at runtime you have a sealed type system, it opens up a completely new playbook, right? So at compile time I would argue you don't need to know, and at runtime you shouldn't know. The decision should already be made. So the time to make it is when you're sealing the type system, and then you make those optimizations. So
there's a kind of two different things here. I didn't hear, I guarantee you performance. So that's one thing. Like if I'm coding in Scheme, I guaranteed get tail call elimination, which guarantees me in practice that I can write recursion that will turn into looping, right? If I fail that, I will Stack Overflow. So it's not even performance, it's just an actual crash.
Right.
I fail that optimization. Must have that optimization. Okay, fine. I don't have that. I didn't hear you say that optimization. So that's one piece. The other piece is that you could define typing compile time to be the point where I sealed and everything before, right? I ended the types here. And where does sealing? Does that mean I loaded the class in the Java equivalent, I did a class for name, I loaded the freaking class. At that point, I got a sealed set of types that were all.
But Java is inherently unsealed. It's inherently encouraging perpetual chaos.
I'm a bad example. I'm trying to come to a point where the program is executing along. It now discovers it wants a new type by name. What it loads is what you call a sealed type. And the sealing happens at the load point where I take what I have and what I'm getting new, and I package it up somehow, and nevermore will inside this black box things change. That's what I understand what you mean by sealing types.
Well, in our design, we don't allow a new type to enter an existing runtime sphere.
As soon as I launch a process, I can never load another type. All types are known at the time I launch a process.
Well, I didn't use the word process on purpose. So,
I did on purpose.
Because within a process, I can create any number of these spheres. So I can always create.
Right. So there's a point which you load. Wow.
It's an insert only, an append only.
Yeah, it's an append only type system. I understand that piece. And it's append only. It comes along. It's not just at the start. It's incrementally. I can append new types.
Right. I can hierarchically add new containers that can inherit arbitrary.
Yes, because a Java is mostly an append only type system as well, but they can append onto an existing type as a subclass.
Right.
And I'm hearing you say no. When I launch worker threads, I remember this part, you haven't said today, but you launch worker threads inside this closed object that has a known type and it can't be changed in type internally, which I think is a very interesting approach. I'm not yet there, and I don't have to make those calls as to what I'm going to do. So I could yet, borrow from your playbook, but it's
yeah,
an
yeah.
interesting thing.
Well, the idea is instead of, so what Java has to do is it has to kind of have a demarcation point, and I think this is what Arto was referring to when you were talking with him earlier. There has to be a demarcation point where you've discovered something new which invalidates some older assumption. So you now have to force that assumption across all running threads. So there has to be everyone has to agree that there's new code to be used and old assumptions have to go away, right? So it's a
this is a piece that is useful independent of any language theory because it's a performance gain of a substantial amount. There are lots and lots of places where it may be the case that something will happen, but commonly it just never does.
Right, right.
That's a performance hack, not a language hack.
But there is also this trade-off on like how easy it is to check speculation. Like, yeah, you can speculate some fact, but if you need to intercept like every single memory access, probably it's not a worthwhile speculation.
You have to pick with care. Yeah.
Yeah, and what is the cost of actually de-optimizing? If you're speculating something which affects every single compile, and then this event happens, well, like you need to take down everything you compiled and recompile the world. Also not a worthwhile speculation. So like you cannot, I don't know how much you can do, but there are trade-offs here.
Okay, so this is the same problem as the hardware guys argued about for caches forever and a day. Some things got fast on average, but some things blew out and missed in cache and were slow. And that, and we can't do that because it's not uniform performance. And no, the statistical average says you win on average, you take it, but sometimes you lose. And so your performance model becomes more complicated because sometimes you lose. But on average, everyone wins. Some people lose.
Well, I would say it depends on other variables. So in our case with slow final tier compiler, we don't want to recompile everything, right? If something rare happens, just the cost of recompiling everything is prohibitive.
Okay, but back up. So you should just do the math. If I have a point where I have to recompile everybody, but meanwhile, 90% of the people ran 1,000 times faster and 10% of the people took a 10-second hit and then they ran fast again, is it worth it? Oh, I think the large count of people would say yes. So just replace people with, I'm doing performance analysis of a large benchmark suite. I take some hits for recompiling. That adds to my bottom end cost. I win because I did some cool optimization that won most of the time. That adds to my, that improves my bottom end cost. Those two balance out somewhere and you draw your line. That's the right way to go after that one. Having said that, things that force recompiles of everybody are basically don't exist because as soon as they're going to recompile everybody, they've already failed over and over again and you fix that and you went on. I've never seen any change that caused everybody to recompile.
Well, I have an example. It's not to recompile everybody, but it's a widespread impact. There is this known issue with interface types in Java. They are not verified, so you cannot assume that you cannot use statically defined interface types. So, and the problem is that the type safety in runtime is checked at use point. So if you have invoke interface, you need to check that the receiver actually implements the interface, but there is no checks on propagation. So you can store objects of incompatible types to interface fields, pass them as parameters, things like that. So one of the things we can do, we can have some kind of extra step after verification, which does verification for interface types using adequate type system. But then we cannot simply reject classes which fail this. So we need to speculate and say, okay, now we've seen something bad, but because of propagation, like we've seen some class which misuses some passes instance which doesn't implement interface somewhere. Now, because it can propagate basically anywhere where this type is used, well, we'll need to recompile a lot of the code.
I claim I went down many paths like this, where things may fail, may not fail, may pass, may not, and you just had to find the cheap place to do the test and cut to carry the invariant where it was useful, but not be expensive elsewhere. I solved it in some instances and I didn't in others. And I just
It's doable. I'm just pointing out that it's not trivial. There are trade-offs which we need to think about.
But there are many cases that are trivial and are super productive to go after. So I'm saying as a general theory, the whole speculation is like wildly useful.
Yeah,
in
and also
some instances it doesn't work.
And also speaking of this issue, okay, we can make most things faster, and then if we slow down like some small percentage, it's okay. Well, like on one hand, I buy this argument, but then we do have some customers which come and say, hey, we have this spike in latency, and we look and investigate, and it's because there was some like deopt events and recompiles, and it caused them to have slow transactions. They are unhappy. They say, well, fix that.
Right. So this is your customer base though saying I want low latency and average performance, and I'll give up on peak in order to get better latency. Right. This is like the GC guy's been through this for decades. You know,
well,
on peak for latency or not.
Usually customers want everything together. Yeah. They want high performance, good latency, and then you need to find like some sweet spot there. Well, you know, we can.
You have to engineer what the customer will keep paying for. Some of it is engineering our expectations. Yep. You can give up this if you want that, and we'll go back and forth, but you can't have them both. And then they'll be like, but, you know, laws of physics. Sorry, guy. Take some of this or some of that, but you can't have some of both because those two are mutually exclusive. And that's expectation setting.
Yeah, and
that would be your sales guy's job. You need to.
I would say that
sales guy.
I would say that was different compiler, was slower compiler. The trade-offs shifted a little bit because with C2, most of these deopt events they went unnoticed because C2 can recompile fast. In case of a Llvm-based compiler, well, in some cases it's noticeable because it takes time to get this method back to.
Can you fall back to a C2 method?
We don't.
Classic tier. You just fall back to the prior generation.
Well, I think realistically we will probably have several tiers of Llvm-based compiler. So it's just to have one compiler in the code base and don't maintain three completely different compilers.
When I was at Azul, I had both C1 and C2, but we could roll back to C1.
Yeah,
that was handled. You need to make your choices though. You got to deal with the runtime, the infrastructure, and everything else. I understand.
C1 is the kind of blocks of code cut and pasted on top of each other one.
Yeah. It's better than a template style, but it's very fast spewing out of bytecodes to IR, doing local IR modifications, and like a linear scan allocator, and much less of aggressive inlining rules. There's a bunch of things that cut way back on. So roughly speaking, C1 compiles 10 times faster than C2, and C2 maybe 10 times faster than Llvm. I'm not sure what the ratios there are.
Yeah, that sounds about right. Although I think C1 is even faster. Maybe even like 2 orders of magnitude.
When I was testing before, they were hovering around 10, but they could have gotten worse with C2 because that wasn't ever the metric.
The measure I had, which was 5 years ago, but was because when I was still involved there, the speed that they could read off of Flash, they could compile it with C1 faster than they could read it from Flash.
Yeah.
So the limiting factor was actually. Even with Flash, the limiting factor was I/O.
Right. Yeah, that's expected at that level of compilation. The other difference is that C2 is about 30% runtime faster than C1 on average on the code, 50% on a RISC, 30% on an x86. So an ARM's probably in the 50% number faster, which is why people cared for the C2. I don't know. Do you have any good numbers on the Llvm versus C2 ratios?
Well, it's we usually look at S-curves where we have all of our workloads. We visualize the ratio, and then we have it sorted. So I would say we have a small tail, probably 5, maybe 10% of workloads, which is slower than C2, and everything else is faster. And on modern code, it might be like quite big difference, like 2, 3x.
2 to 3x in some cases.
Yeah.
Okay.
It's usually where you have a lot of abstractions, a lot of fluffy code, which with more aggressive inlining, escape analysis, you can eliminate all these extra layers.
See,
that's where
pretty aggressive inlining, but it misses on escape analysis. At least it missed up to some years ago. It was still missing escape analysis of any sort.
Yeah, I think what happened is the idiomatic Java code changed. It became more fluffy, and it's just now there is more to work for an optimizer.
Yeah.
Because if we look, for example, if you look at spec, I think
are you running, which version of Java are you comparing against? Because I know the C2 has been under active development still at Sun, at Oracle.
Well,
yeah,
we're comparing
8 or Java
8 and 11 are
11. Okay,
yeah.
And you're still seeing those numbers on 11.
Yeah.
Okay, fine. Because I know escape analysis was coming, reasonable escape analysis was coming, but I would have said post 11. I thought that was 13, 14, but I don't know where they're at. Fine. Okay, that's good to know. Yeah, I didn't expect them to be uniformly greater or lesser, by the way. It's always the case you get a distribution for every workload, and some are better, some are worse. You just want to be on average better. Cool. And you're slower yet again. But I mean, C2 could inline more aggressively just turning a knob, which is why I was asking, is if somebody had been paying attention, that knob may have been turned.
I think actually in OpenGDK upstream, they are changing the defaults to be more aggressive. And I think this reflects the fact that, well, workloads become more complicated. You just need to inline more. There's
in deeper. Yeah, it makes sense. Okay, cool.
Well, and then like it's easy to say, okay, it's just inlining and escape analysis. But when you start looking into performance issues, there's a lot of things, just the quality of optimizer. Like a lot of small things overall, they give you good performance. So sometimes it's hard to say what exactly it is in Llvm, for example, which helps this workflow. Like maybe there was something small missing, and I can see it looking at when we have gaps, for example, with C2. Sometimes it might be something small and trivial, which we just for some reason don't do. You fix this small issue, and then everything kicks in, and like you get good performance.
It's always the case. Somebody has to be paying attention at Sun side, Oracle side, to make that keep working on those things. I'm surprised you get 2x in a lot of workloads, but I can imagine if things have changed and no one's paying attention on the Oracle side, it could go there. Matt, the deal with user annotations for optimization is simply that you have to check them that they're valid. The check time has to be cheaper than you doing the analysis yourself. There are sets of optimizations for which the analysis cost can be very expensive and the check time can be very cheap, and then you also have to get a payoff out of it. So we had this discussion came around more than a decade ago, more than once. A lot of folks were like, "Hey, just do this and say whatever," and the answer, of course, is I can't take an annotation at face value. You can just lie through your teeth, and that breaks the security model. So you must check them.
Yeah, and it's not just that if the annotation applies to one particular workload and you end up, for whatever reason, with a different workload at runtime, then your best information is obviously the information you have while it's running.
Information you have in your hand, yeah.
So just to clarify, it's not necessarily saying that you are sure that you have soundness, that you are going to have correctness for the optimization, but only pointing out the potential points where, for example, speculation may make sense. Right. So it's a may analysis, user providing basically may analysis result, but not must analysis result. So for example, when you have something, when you load configuration value at program startup, something is true or false, and then for the remaining run of the application is going to be true or false, it is at this point, this single branch that you can annotate, speculation may make sense here, and that's it.
So as soon as you load
so you are going to pay performance if the speculation is wrong, just as with ordinary speculation, but you are not going to introduce soundness bugs. So not breaking correctness, basically.
So as soon as you load a config and you get constants out, those get folded typically by the compiler right away.
Yeah, this is talking GCC though.
Yeah, GCC, so ahead of time context.
Okay, fine.
And to my knowledge,
Well,
Linux kernel uses something like that for a few configuration options, I think, in the drivers. So there are cases where it does pay off in a relatively constrained environments.
So I have seen people try this in the Java world a long time ago about throwing down annotations that the compiler was supposed to take verbatim, and obviously couldn't. But then there was a long look for annotations that were profitable, and not very many profitable annotations showed up that were cheap to check and led you down an optimization path. I could imagine inlining being one of them, where I wanted an inlining keyword to force. We tried inlining keywords at different times, and they weren't necessarily helpful. People would do it in the wrong place. But I certainly have coding paradigms, coding styles where I badly wanted inner loops to be inline to their limit. And that required massive loop and switching, and it was worth it. And it was well past the JIT threshold, and they wouldn't do it.
Yeah, I think it's a different trade-off in a JIT world, although it could address the Arthur's dilemma. If you have a customer that simultaneously demands latency and bandwidth, then you essentially offload the decision to the
client.
Exactly.
Yeah, okay. That's setting expectations away.
Yep.
Yeah, totally. Okay, guys, your problem now. Flip it left, flip it right. What you want to do? And they'll love it, because if they're power users, they'll eat it up. Like, okay, I get to play this now. It's my problem. And then they'll give up on it after a bit because they flip the flip and they know what happens, and then they're comfortable with what they did. And it didn't matter. They didn't make their situation any better. They feel better. So they keep paying you money. So it's a good business call. People are funny. My coffee's empty. Well, here we are. It's 11:30. We've gone an hour and a half. Does anyone want to ask something else here, or?
I definitely want to hear more from Yorick in the future in terms of what he's found with the various approaches. This to me is one of the most interesting parts.
The GC.
Well, with respect to the decisions around construction and
finalizers,
all that stuff. Yeah, I mean, it's very interesting to me.
Yeah.
And
yeah, well, I'll be here more often, so
and dragging whatever great ideas you can find in Erlang or elsewhere. So
yeah, actually, I'm also in that zone of sorting out what to do with finalizers and final fields and constructors and the like. And I have my take, but I'm not wedded to it. I don't know the best answer or anything. I'm excited to hear alternatives. Okay, well, this is fun. Let's go do this again next week. As before, I'll put it up on Twitter here within a couple hours, and hope we all have a happy holidays, whatever that means, in the different parts of the world here, and see people again. All right, bye-bye.
Cheers. Bye.
Bye.
Oh, you raised your hand? No, you clapped, I think.